Okay, let's talk a little bit about first order half-life. First order half-life ends up being more important because radioactive decays are also first order. Not that you can't use the other ones, but far and away this first order half-life is the most common. So this is based on the integrated rate law for the first order reaction. So the half-life is the time it takes for the concentration of the reactant or amount of reactant to drop to half of its original value. We're going to call that half-life T sub 1/2. And it's taken to be time for A at time 0 to reach 1/2 A at time 0. If you plug those values into your integrated rate law and solve for time, you would get T sub 1/2 equals natural log of 2 divided by AK, which natural log of 2 is approximately equal to 0.693 divided by AK, where A is the stoichiometric coefficient. For radioactive decays, you can drop the coefficient, but for chemical reactions, you cannot. So here's one for pressure of, looks like CH3NC, and you can see after about 12 15 seconds it's dropped to about half the original value, and then again it's dropped another half, so on and so forth, and it drops by half each time. Usually after 10 half-lives they say it's pretty well gone. There's not going to be enough left to worry about. So if we say the half-life of iodine 131 is 8 days, what fraction is left after 24 days? And so we're going to use even half-lives. So we're going to say our half-life is 8 days, and our time is going to be 24 days. And so we should be able to work that. And so how much is left? What fraction is left? So if we got our time here, so what we got to see is how many half-lives is our time compared to our half-life. So if we say 24 divided by 8, that is equal to 3 half-lives, which means I would divide my original amount by 2 3 times. So if we got 100% of it at the beginning, we're going to divide that by 2 3 times, or 2 to the third. Or you're going to say 100% divided by 8, because 2 cubed is 8. And so you're going to say 100 divided by 8 is 12.5% of the original amounts left. Since I didn't say a certain number of grams or a certain concentration present, I just said what fraction, that's the best we can do. It's going to be 12.5% or 1/8 the original amount. And that's really all we can say at this point. Okay, let's look at another example. Let's say we got a radioactive isotope and it decays with a rate constant of 1.00 times 10 to the negative third days. We want to know the half-life T sub 1/2. We had our handy dandy formula for that, so we should be able to calculate that based on the rate constant. I've already transferred the information to the paper, so we got natural log of 2 divided by 1.00 times 10 to the negative third days. And then it's just running that through your calculator. You can crunch out the 0.693, but I find it's more accurate to just use the natural log of 2, since the calculator will handle that. And so we plug that into our calculator. We're going to get T sub 1/2 equals 693 days. For sig fig purposes, since we're talking about half-life, this 2 is considered to be an exact figure, so we're only basing the sig figs off of the rate constant.